Hello there. This is a video absolutely no one asked for, but I'm gonna do it anyway. So, the other day on stream,
This
Cosmoem,
happened.
Celesteela, and Groudon? Really? Cosmoem? Insane. And then it got me thinking, how dense is Cosmoem? Now, for the record, I'm not a mathematician, I'm not a physicist. I'm just doing this for fun as someone who likes math, likes Pokemon, and has failed physics enough times to not forget the basics. Alright, so to start off, we're going to need to know a few things about our Pokemon Cosmoem here before we start doing any kind of calculation. So, what we're going to need is Cosmoem's dimensions, and by that I mean its height and its mass, which I was able to get from Bulbapedia are zero point 0.1 meters and 999.9 kilograms. So, how does this apply to our actual Pokemon? Well, we know that it's going to be about 0 0.1 meters across, and judging by the image and by how it's kind of drawn, we can kind of assume that it's about equidistant all around. It helps that there's a sphere in the middle. So, if you go back to my stream, what we did was that we put this into an image processing program, used the ruler function, looked at, gave the entire length here a certain distance, which I set to about 12 centimeters in unit measuring distance, and we found out that the sphere in the middle is about half that distance, so about 6 centimeters on the ruler, which means that it's going to be half of the 0.1 meters, or about 0.05 meters. Now, the reason why I did this is because, much like a star, I'm assuming that our complex ellipses, such as these, and so we're just going to simplify it and do our rough estimates around the core of Cosmoem, which I'm making the assumption the most mass is located. So, for sphere, our volumetric formula is going to be 4 over 3 times pi times the radius cubed. Now, we have the diameter, which we calculated previously, to be, well, this is wrong here, but 0.1 meters instead, which means, and my units are off again, that the radius is 0.05 meters. Throw that into our calculations, and for our volume of our central portion of Cosmoem, we're going to get 6.55 times 10 to the negative fifth meters cubed. Now, to calculate for density, the density formula is going to be mass divided by volume. So now that we have our volume, we're going to be able to actually run our formula through because we already have the values for this, in which case the mass is again 999.9 kilograms. Our volume, which we just calculated, 6.55 times 10 to the negative fifth meters cubed, which, plug and play, is going to give us a density value of 15,265,648.85-ish kilograms per meter cubed as our density for the central ball of Cosmoem, which obviously is on the conservative side. Now, in comparison to actual stars, getting this information off of Wikipedia just as a quick search through, our density for a white dwarf, for example, is going to be anywhere from the range of about 10 million to 10 billion kilograms per meter cubed. Now, if you look at the source, it does say 10 to the 4th to 10 to the 7th grams per centimeter cubed, but if you do the conversions to kilograms per meter cubed, it's going to multiply that up by several degrees, which means 10 million to 10 billion kilograms per meter cubed. We've shown that this little guy is actually a complete monster and would probably be incredibly hot due to the densities occurring within its body, and definitely not carryable by Lily or Ash. So, if you like this video, remember, like, comment, subscribe. I hope you guys enjoyed. This was just all for fun, so if you guys are actual mathematicians or physicists that can do and calculate these things better than I can, please, I'd love to hear from you. But in the meantime, you can catch me having fun and doing these kinds of things on twitch.tv/obtusetrigger. Jump by, have fun, take care, y'all. Peace.